Welcome to The Explainer. Today, we're going to talk about a single concept, one simple measurement that connects something as huge as a bridge to the path of a tiny ray of light from a distant star. You know, it really does sound like the beginning of a bad joke, doesn't it? But the answer is actually this incredibly powerful measurement that, and I'm not exaggerating here, literally builds the world we live in. The answer is they all bend. They all deflect. And by measuring that tiny, sometimes completely invisible movement, we can learn pretty much everything we need to know about its strength, its health, and yeah, even the fundamental laws of the entire universe. So let's start right here, on the ground, with the massive world we've built all around us, the stuff we rely on every single day without even thinking about it. See, for an engineer, deflection isn't a problem. It's a vital sign. It's a feature, not a bug. When a bridge sags just a little bit under traffic, or a beam in a skyscraper flexes, that tiny movement is telling a story. And if we can measure it precisely, we can know for sure that our designs are working. And, most importantly, that everyone is safe. What's so cool is watching how our tools for this have evolved. I mean, we started with simple, direct mechanical gauges for a one-time measurement. But now we have things like a falling weight deflectometer, which is basically a giant controlled weight that we drop to see how a runway or a road responds. Or we use real-time sensors that are constantly monitoring a bridge's health, almost like an EKG for a massive steel structure. It's incredible. Okay, but what happens when the thing that's bending is so small that you can't even see it? Well, that's where this whole concept gets really, really interesting. Because this is the point where we go from just ensuring safety to actually driving innovation. We're not just checking if something is strong enough anymore, we're using these tiny bends to figure out how things work at the most fundamental level possible. And just look at the wild range of applications here. It's the same exact principle. That tiny, imperceptible bend or warp in a microchip from heat tells us if it's about to fail. We can even measure the precise force an orthodontic wire is putting on a tooth to straighten it. It's the same idea as the bridge, just shrunk down to a microscopic scale. So how in the world do we actually see these invisible bends? Well, we use some seriously clever tricks. One method is basically like using super high-speed cameras to play a game of spot the difference on a surface, which creates a map of all the stress. Another method can actually detect the tiny, tiny wobble of a laser beam when a material heats up and expands. They're just incredibly advanced ways of measuring that same simple thing, a bend. All right, so far, this all feels pretty down to earth, right? It's all about engineering, materials, but believe it or not, this exact same principle scales up, way, way up, helping us understand the very fabric of the universe itself. For hundreds of years, the answer to that was a definite no. Of course not. Light travels in a perfectly straight line. End of story. But then, a radical new theory came along that was about to change physics forever. The whole debate really boiled down to this one profound question. Is gravity a force that pulls things together? Or is gravity a bend in space-time itself, caused by a massive object? Because if it's a bend, then even something without mass, like light, would have no choice but to follow that curve. And then it happened. During a total solar eclipse, astronomers aimed their telescopes at the sky. They waited for the light from distant stars to pass right by our sun, and they saw it. The light bent. It deflected, exactly as Einstein had predicted. It was proof, right there, that gravity literally bends the path of light. And this isn't just some old story from a history book. We use this principle as a tool today. Astronomers use incredibly powerful instruments to track the deflection of massive solar flares as they erupt from the sun. By measuring that bend in their path, we can actually predict space weather that could affect us right here on Earth. So we've gone all the way from a bridge to a microchip to a star. Let's pull this all back together and talk about why this one single measurement is so unbelievably important. So just think about that for a second. The simple act of measuring a bend is at the heart of everything. It keeps our bridges standing, it helps build our computers, it makes our medical tools better, and it unlocks the deepest secrets of the universe. It's so much more than a measurement. It's like a universal yardstick for understanding our world at every single scale you can imagine. It's just an amazing reminder that sometimes the most profound world-changing insights come from looking at the simplest things, just with more and more precision. Thanks for joining this explainer.